Bom dia neste frio. Obrigada pelo cachecol. Então, we go here for our third lecture. Don't know why I take this out. It's crazy. I cannot see my window, my screen. Okay. So we are in our third lecture, and just for curiosity, how many of you are working in an extragalactic field? Okay, and the solar system and sun and planets, and the Milky Way, stellar. Okay, good, thank you. So, let's go. We have 4 lectures. If somebody missed the rest of if you miss everything and you're here just arriving today, I don't know if this happened to somebody, we are going to talk about the galactic bulge of our galaxy. So, the stellar populations in the Milky Way bulge. We have written a review for the annual review in 2018, which is here the reference. Beatriz Barboui, myself, and Ortwin Gerhard. We are from 3 different expertise. Beatriz Barboui, an observer, and very much linked to data that show the bulge is old. Me in the middle of the two. I will explain how. And he more into dynamics and also data, and very much in the side of formation of bulges from disk buckling. So more towards younger bulges. And lots of discussion. And that's what was very enriching to write this, because we didn't agree. So we had a lot of discussions. It was very hard to write this. So it's useful to see the discussions of the age. There's a section about the age of the bulge. And so all these are not just that we sit here and each one wrote a section. We really discussed until we agree to what we are writing. Okay, so that was a lot of work there. And I cannot cover the whole thing because I wanted to show you what's happening now. And as I said, this all was before Gaia and Apogee, which are the 2 revolutions we have discussed last lecture. And then in the meantime, you also had the BDBS survey, the Blanco Decam bulge survey, which is a photometric survey, but is also very important because it has millions of stars in the bulge. So a lot has happened since 2018. And another thing that has happened for the extragalactic people, so that they don't sleep, here is a nearby galaxy in a recent paper, and this is amazing because using MUSE, we are reaching now this spatial resolution in this image of 100 parsec. And so you're starting to see what we in the Milky Way cannot see, which is the bulge that I'm calling, whatever this is. We have to now, the words we use for the Milky Way are always complex. So the box there that you see that we call the bulge, you see already from this picture that that box contains something in the middle, that could be the bulge, an inner thin disk that's there from where the spiral arms are living, and regions of interface between the spiral arms and if there is a bulge, okay? And there is a bar. In this case, you don't see really a bar, but there is a bar. So what we can see the structure very easy, not very easy, but now, in the next few years, this kind of data will be available. But you still have to study this with integrated spectra. No? So you have the easy way, as we discussed in the first lecture, the easy way that you can see the bulge, the spiral arms, where there is, the distance, and you see that, but you don't have the information individual, so you don't have the time information that we have here. Okay, but this picture already illustrates the point. The bulge, or the box bulge, that in fact in the beginning of the review we defined the box as the bulge, has many things inside. Okay, so we were left with these maps of the Milky Way, the bar is there, and we said with Apogee we can plunge into the bulge. No? So I put it back here for you where we were coming from, when we had only photometry, and if I take the box here towards the bar that we saw just combining photometry and Gaia, we had 30 million in this box. And then from this box, I could fill in the box with Apogee, who arrived here in the box with 30,000. So just there we went from 30 million to 30,000. But we need to do this, and we will decrease the sample, because now we need also, this you have spectroscopy and Gaia, and if I need proper motion, then I'm going to decrease even more my sample. So, and then we were in this plot that we had discussed, and today we are focused here, in this box. This box are the inner 4 kiloparsecs, now, in the radio distance, 4 kiloparsec, and now the lower, a bit lower into the mid-plane, very low here, so around up to 1 kiloparsec up from the mid-plane. That's where we are focused here, because this was the novelty. This data was not there before Apogee. Okay? So, first of all, you see immediately here that the discontinuity is very sharp in the inner regions. This is something that we thought that after you go inside, the things were starting to be a one curve, because the data used to stop here. And this was showing, and instead you're seeing this, okay? So, what we did is that the difficulty here is the extinction, of course. If you're working the bulge, the extinction here is an X and Y, and here is the X and Y, and here is Z, height from the midplane and galactocenter distance, and this is the AV, the extinction magnitude in V band. And you see here, you are above 16 magnitudes in AV. So really very high extinction here, and you still have some apogee data, right? And this is how the galactic center, this height from the midplane translates into X and Y, so when you look the galaxy from above. So we are going to a very high extinction situation with apogee that's in the near infrared. But even like this is difficult, because you have other problematics. Okay, so why we felt that that's the moment to go? First we had the data from Apogee, and at the same time we have the Gaia EDR3 release. And this here I'm showing you a plot made by Anna, the proper motion error that we have, and the parallax error that we have, uncertainty, for the sample of the box, the 30,000 only. No, not the 30,000, the RPM sample that I'm going to discuss you in a while, which is a sample really in the bulge, taking out foreground, and I'm going to show you how we're going to take out the foreground. And you see that from Gaia DR2, that is in red, to Gaia EDR3, in parallax, we decrease. The same sample has the much sharper, you're going to have much better parallax after Gaia EDR3, but a really much better proper motion. So the proper motion error, error distribution goes from the red to the gray, you see? So you have an improvement of proper motion and big improvement in proper motion and some improvement in parallax. That is the hand we have today. Say, okay, we will go to the bulge and we will for the first time attempt to analyze chemodynamics of the bulge. Not only the chemistry, but also to know how this is correlated with the orbits of the stars there. Okay, so that's the goal. First thing we got is that if I have that box of 30,000, and here I'm showing you again X and Y, but now we are here in the 4 kiloparsecs, inner kiloparsecs. So here's the galactic center, the bar, 2 kiloparsecs here, 2 kiloparsecs there. So we are really in the center of the galaxy. And if we plot the radial velocity with respect to us, you see this shape. Okay, and this shape is essentially what is called the quadrupole that characterizes this streaming motion from the induced by the bar. So it's something expected to be seen if the galaxy has a bar. Okay, and we see this very well. And actually, it was this figure that convinced the referee that our distance were very good in this region, because there was the referee, by the way, was James Binney. So it was not easy. And so all approaches and so on, so many problems. Of course, there are many caveats, because we are using Star Horse with Gaia data, but we are assuming a extinction curve, and the extinction curve may vary. We are using one constant extinction curve. It may vary, but if we say in the beginning, because we are looking to this data for the first time, I said, let's not vary everything. Let's go with what we have, and we know the caveat, okay? So a beautiful project would be to, somebody want to join our Star Horse with some fellowship there, is to try the variable extinction in this region. and see what we get. So what does it mean? That we may expect systematics in our distance, depending on the extinction in the line of sight we are. But this plot shows we have a beautiful result and shows that our distance is not so bad. Otherwise, you wouldn't see this, okay? A recent cosmological simulation by Fracuti, 2019, for example, for galaxies that have the bar, see this kind of pattern. So the simulations are all now trying to go for that, but it's difficult for many other reasons. I don't want to discuss. Okay, so that was the box, but I want to be sure I don't have disk stuff in front of me, so I was afraid exactly of this point, that we may have systematics because of extinction. So we can do a different way that's not relying so much in our distance. And the different way is to use this, that's called the reduced proper motion technique. It's essentially a magnitude that will depend on the H magnitude of the star and will be dependent on the proper motion, okay? And with that, just by using the reduced proper motion technique, we can go from the bar bulge sample, which is what I was showing you, the box, to the RPM sample, reduced proper motion selection. And when you do that, you see that in velocity, you get a bit rid of the stars that are thin disk, because they are 220. So the blue is more biased to high velocities, V5, which is rotational velocity, than the red. And what is important, this translates like this is the distribution of stars in that box, the distance from us, from the galactic center. You see you have a lot of stars in the front of the bulge. And this is what you get after you use this. And this is the proper motion distribution of the RPM selection versus the proper motion. Essentially, you get rid of stuff that have too high proper motion to be there. The problem, the downside of this is that here you have all the stars in the box in green. Here you have number of stars versus height from the midplane. Here is 0 on the midplane. Here is above the midplane, below the midplane. And so you see that you have a bunch of green here that's not blue. Why? Because for the blue stars, you have also Gaia information. For the green stars, you have only apogee information. And what you're seeing, you are missing. There will be stars when I get very close to the midplane that have only apogee but does not have Gaia. Okay? So this is a whole study of the sample before making conclusions, right? This is key. Okay, so now I show you the box. Remember, apogee we have high resolution spectrographs, so we have several chemical elements, right? So here again is the height above the midplane, above and below. Here is not so below and above, and according to the galactic center distance, using star horse distance. And now I'm coloring this by metallicity, okay? And first of all, you're seeing we are getting less data here. And then you see this metal-rich stuff. And you're already indicating, wow, this is really above solar. You have a lot of stars that are very metal-rich here. And as I told you in the lecture 2, we see super metal-rich stars here that we need to see where they came from. And so here you're seeing you have a lot of reservoir of stuff that could come from there. And then you have also metal-poor stars everywhere. Okay, so that's more or less what you have. But these plots are very dangerous to analyze because when you to reach here with apogee, which is a small telescope, the Sloan telescope, we are above the clump in the giant branch. We are in the tip there, where everything is dangerous in terms of spectra pipelines. Okay. But anyway, so we were very afraid of everything in this data set, and then we got Bini. So here is the same plot. Now, when I do not use so this is when I'm not using the full box of the 30,000, but now I request the proper motion, okay? And as I showed you before in that other plot, that's the whole you get. And so how are we going to proceed? So again, to address your question of the limitations of the data. So we have a project which is called Gaia Infrared, which will be the next Gaia that will give in 20 years better proper motion and everything. But on the top of that should have a near infrared detector to go and peer into that region. Okay? That's a whole other story for the last lecture. Okay, so now I have this. Now I can plot the same old alpha variance versus iron plot that you are now tired of hearing about. 26,500 stars below z equal 1. And you see this thing. It's not a linear thing. This was already people, it was not easy to put this out. And then if I use the RPM and want to look really the new things, I'm going to down now to 0.5 kiloparsec from the midplane. How many stars I am left with? 3,800 stars. So when people say, oh, but your survey already measured to 500 stars, why you need that? Because of this. We are back to 3,800 stars, and I have all the stellar populations mixed here, and I have to open up in different families. So I need at least 70,000 stars here. And that was a project we applied, and today we got very bad news, but tomorrow we'll talk about that. So, this one, of course, has less foreground and have proper motions, have good distance. So what can I do? Orbital analysis, okay? Because without good distance and without proper motion, no orbital analysis. Now it comes the complication. So please bear here with me. I need, what I say, 7D plus information. So I have the 3 velocities, and I have the distance, and I have plus for chemistry. Because this is a full data cube. You have all the chemistry. And now let's see that I take those. So what I did, first I relaxed. I had 3,600 stars up to 0.5 kiloparsec. But now let's take 1 kiloparsec, okay? When we do that, we go to 8,000 stars. It's not so bad. So we have 8,000 stars in this. Remember, all these stars here are inside the galaxy. Now, that comes the danger that in chemical evolution and in the analysis of galactic archaeology has been a problem. And actually, we have been working a lot of there. One way, what is the problem? That to disentangle the thick disk, the thin disk, the bulge, the properties of these components are not there beautiful like we do in. They are overlapping. And if I do and say, high alpha thick disk, low alpha thin disk, but depending where you cut in metallicity, you already may get wrong results. So actually, I have a whole bunch of work, and we are doing a whole bunch of work using machine learning, like TSNE, other like to reduce the dimension. There is a poster there. I saw you also using that to help that the TSNE looks these 7D plus dimensions, all the chemical elements together. Because here I'm still working on alpha over iron, and I don't need to do that because I can go to neutral capture elements, high light S process, heavy S process. I can go really nuts here with chemistry. So that's why instead of say let's cut here who is thin disk, who is thick disk, no, it's dangerous. So instead of that, we project the whole sample in a Zmax eccentricity diagram. So Zmax is the highest point in the orbit. Because I see a star today at 1 kiloparsec, but if it's a halo star passing here, this is not a bulge, this is a halo star, right? But the Zmax in the orbit tell me where the orbit is confined. That's why it's important to have the orbit, okay? So Zmax is an important thing, because everybody that's Zmax 1 here, below 1 here, these people are really orbiting and staying inside that 1 kiloparsec, okay? Okay, so Zmax is very important. And another parameter is the eccentricity. Okay, so very high eccentric stars tend to be either debris that fell in here, or also stars that I'm seeing, because remember I have a hole in my sample. So to see somebody that is a 1 kiloparsec very close to the plane, I need it to be eccentric and be here. Because if it's low eccentricity, I'm not getting there. I show you I have a hole in the distribution. So I need the high eccentricity star will bring me to see stars that are born there in the very 1-2 kiloparsecs. That's why this diagram is the diagram I like, okay? Now, here is the density of stars in this diagram, and we broke it in windows, 9 windows, okay? So when you walk here, eccentricity goes from 0 to 1, so these are very high eccentric stars. And when you go from here, eccentricity is the same, everybody's high eccentricity here, but you are reaching orbits that reach very high Zmax, Okay? So what is here? Well, orbits that are very low eccentricity, low Zmax, they are thin disk-like, but in the bulge. Okay? When you are here, they are orbits that are a bit high Zmax, intermediate eccentricity, they are thick disk-like. But I'm not gonna cut and say, here's thin disk, here's thick disk, because everything has a bit of everything, you see? So this is the clever way to go for. So now, instead of showing you in density, I'm showing you in metallicity. And you see again that the more you go to stars that cannot leave much the orbit, do not go much up, the more metal rich you are. So when you say the bulge is metal rich or metal poor, I have to tell you, depends where, which orbits, because you have a population that is very metal rich, and this population is confined to the bottom. It's not leaving much in Z high direction. While the metal poor population, if I take out the metal rich from here, the metal poor population you see is everywhere. Okay? So the bulge is metal poor or metal rich? That's the wrong answer, the wrong question. Okay? That's the main point here. So here we have, from what I told you, we have stuff that the orbits indicate they could be inner thick disk, inner thin disk, and old spheroidal bulge could be there. It's not easy, but I don't have only this. I have more, okay? So what do I have? Same plot, don't get scared. Here is Zmax box, eccentricity, the same 9 box we were looking after, so I put it here so that you see this. Now, for each of the groups in the box, I plot the alpha over iron plot, because I have. The stars that are in that box have alpha and have iron. I plot alpha over iron blocks. So, first thing you see dichotomy almost everywhere except here, okay? But now I am left with 200 objects, a problem, okay? Again, statistics will give a problem. I'm complementing this with 2 other papers that will be very beautiful. Here is where most of the data is. High eccentricity, low Zmax, because I'm using apogee. I'm looking to you saw from the maps, I'm looking like this to the bulge, no? So, what do I see? This plot is complex because you have alpha over iron for each plot. And they are colored by the probability of the star to be in a bar-shaped orbit, because there is still this problematic. I told you have the thin disk with velocities, rotational velocity, and in low Zmax, then you have a bit more high Zmax for a thick disk that lags the thin disk, so rotates lower than the thin disk. You can see this from the data. And then you have that some stars are in the bar. The bar is not a sum structure there. The bar are stars making orbits so that you see a bar. Okay? So bar in bar-shaped orbits, I can compute that with some errors, of course. So I color here, thanks to Angeles, Pérez Villegas, who compute these orbits. I have the probability, because there are a lot of uncertainties, you can imagine, because I need to know the potential of the galaxy, little detail. So the probability to be on a bar-shaped orbit, the more is a probability is high, so I believe, probability means I believe this is a bar-shaped orbit, okay? It's red. And the ones that do not seem to follow bar-shaped orbit is blue. So the first thing that for some people were surprised, and was actually for me was exactly what we had to find, is that if I go in this box here where I have most of the data, I have 3,000 stars here. In a sample of 8,000, I mean, people are sitting here a lot. Eh? In this sample here, I have, first of all, high alpha and low alpha also. And the people thought, okay, when I am there, I'm very metal-rich, you see in a while, I should be dominated by bar, and the bar should be all low alphas. No. The bar should not be all low alphas. The bar has high and low alphas. Okay? Because the bar is not a stellar population. The bar is a structure that was formed with picking up stars that were there. So they pick up whatever was there. The star that's forming at some point and the star that have formed before. And they can be trapped in the bar, for example, right? So there are red points down and up. Okay? So bar, the way to say this is that the bar has no chemical segregation. That's the result, okay? Okay, now comes another thing that's very interesting in this data set. The stars that are here in these boxes here, which mean all eccentricities but do not leave much the disk, they are in cooler orbits, we call. They are not so hot kinematically because they still have rotation, right? It turns out that for other processes that I'm not going to discuss because I'm not a specialist in dynamics, it turns out that a star to be radial migrating, to kick out to a different angular momentum and to born here and going there, those that we saw at the solar vicinity with high metallicity that we think came from there, turns out the stars to radial migration have to be in cold orbits. If you are too hot, meaning kinematically hot, rotating little, and too high, you're not migrating. Okay? So that's why I call these the migration candidates. Okay? Migrator candidates. Can somebody from here migrate? Maybe yes. You know, I don't know. But I'm talking about in general. These are my migrator candidates. And these here, the very eccentric things, they're very eccentric. If there is a bulge, which means a spheroidal bulge, which means a not rotating population so much, there's where it should be. And maybe it's buried in this bar and disk and everything that's in front of it. And that's why people say, oh, our galaxy doesn't have an old bulge. It's only a bar. It's only a thick disk. And the question here is that, is this true or not? Okay? So here is where I think, I don't have ages. That's the problem. I don't have ages. Here is where I think the old spheroidal component will appear in this sample. Around the very high eccentricity, because it should be a hot component kinematically. And if I go up, I see it more clearly because I have less bar and has less disk in front of it. Okay? But for this sample, it will be difficult to see it. Okay, so now I can take, now this is this piece is down here, okay? I'm taking this piece, these 3 windows, low Z max. And now I can, so that's why I wrote here, the Z max below 1 here, and all eccentricities. Eccentricity increasing to this side. But now I have more information. I have the metallicity distribution for each of these windows, okay? And when I look here, remember, this window were the people that would be mostly dominated by inner thin disk stars, stars that are rotating, low Z max. The metallicity distribution is like this. Has a peak here. Is similar to our solar vicinity, but it's shift because the peak here is 0.2 dex. Okay? And now, if I look to what happened to the more eccentric stars, of course there will be a part of the population of disk maybe also interfering here, especially those that are trapping the bar. So you cannot say, okay, when I move here the thin disk is gone. No, part of the thin disk could be in the bar, or could be even reaching here. But what do you see? You see that you have a very high metallicity people sitting here. They are on the bar. The metallicity here was already high, but the peak here is 0.2, here is 0.25 in log. So this is really where the supermetal rich stars are sitting, you know. And in between you have in between. You have in between things. That's why it's complicated. Okay, so we find a clear reservoir of metal rich in cold orbits. That's why we believe if we find the supermetal rich here, why not being from the bulge? Which means another way to see radial migration. You see? So things starts being more, I'm not using any model here. I'm going for the data, okay? And the data is telling me, hey, the supermetal rich stars exist, they are in the inner galaxy, there are a bunch in cold orbits, and this bunch can migrate. Okay? How will we migrate? Who migrate? How's the bar at that time? No. This is a ton of paper discussions and fights in conference, okay? But the data drives the discussion. That's why I was fully theoretical in the beginning and I became more data driven, actually. Not to say bad about theory, because if you have a good understanding of the theory, you know how to analyze this data, okay? So now, remember I cut the bottom 3 windows. Now I'm in those windows where I think I will discover the old bulge there. So what are the windows now? all the high eccentricity part. So all these stars have high eccentricity and are in all heights from the midplane, okay? What you see here? So you see a weird thing here happen. You almost don't see a double thing, but this is the kind of situation a paper where you say, I almost don't see, I think it's a one go, but then somebody say, just sample your sample number and you see, would you still fit something like this? Because you have just low statistics. It looks like 1, but could be 2. Yeah, so I don't have an answer for that with this sample, okay? So my feeling is that here should be a 1 go, and if it's a 1 go, it's a bulge, but okay. Let's go here. What's the metallicity, like I did for the oil, how the metallicity distribution change when you go from low to high for the high eccentricity stars that are in the inner galaxy? So don't get lost, I'll say again. How is the metallicity distribution of the stars going from stars that cannot leave the midplane to high above the midplane, all of that eccentric? How is this metallicity distribution? In the inner galaxy, because they are in the inner galaxy. Actually, if I compute the mean radius of the orbit of the stars, because I have apocentric, pericentric, I have the orbit, no? I can see that the guiding radius, which means the mean radius of this star, a star that's very eccentric, has a guiding radius, a median radius, and this median radius is around 1 to 2 from the inner galaxy. So as I told you, there's a lot of stars in the inner galaxy. I have a hole in my sample, but I see them if they have high eccentricity, and I'm seeing a lot of them. The guiding radius of the orbit is 1, 2. So these stars are doing something in the innermost 1, 2 kiloparsecs of the galaxy, okay? And what you see the metallicity distribution I showed you before. You see this metal-rich thing in the bar. As you go, this thing will get less important, but the metal-poor stars are there, and apogee was not very good for metal-poor stars, but it increases very clearly as you go up, okay? So you have a population there that look like a spheroidal population. It has a velocity dispersion. I have velocity dispersion for this. Has a velocity dispersion above the one you expect for the thick disk. Remember I told you we have the thin disk, the thick disk in the other lecture. Thick disk goes around 40 kilometers per second, the velocity dispersion. Here, the velocity dispersion is huge. So it's like you are in a spheroidal component, okay? But look, we have 200 objects here. And I'm saying they are not sitting here. They are everywhere, but they are buried into the bar, okay? Okay, so if I am correct, these stars here, sitting here, a lot of them are the oldest stars of the Milky Way that are buried in the inner kiloparsec. And they are surrounded by a bar. And that's why when people look only without orbs, they say the bulge has only a bar and a thick disk, okay? You have really to dig in the apogee data to find the bulge if you're using this data. Okay, so my idea is that if you have this old spheroid here, you are talking about something that formed very old, 13, 12 gigayears. We are at redshift 5, okay? So it's the redshift 5 in the inner of our galaxy. Okay, so let me make a toy model. If I make a toy model where I put, as a comparison, something we call halo, but the halo essentially do not exist anymore. This is another discussion. But if I do a very fast enrichment here of the star formation, this is time metallicity, and here is just 500,000 years. Remember I told you the thick disk was reaching its metallicity in less than 1 gigayear. We could date that because the thick disk was a year. I cannot date the bulge because the bulge is there and I don't have ages. Okay, but let's make a toy model then. I make a chemical evolution model, and this is an inhomogeneous model. Remember I told you there were different kinds of model. So this is an inhomogeneous model where things do not mix immediately. Instantaneous mix is not used. Okay, so I make something that forms very fast with a lot of efficiency, and I have this metallicity distribution, metal rich. I have an old bulge. And I have that the peak is not at 0.25, but the peak is around -0.7 or -1. And then what is interesting, if I just take these two models, this will be a halo model, metal poor, and a thick bulge model. The important thing is you do this such that you have a metallicity distribution to fit the data. Okay, so this is a 3D. These curves here are a 3D dimension. You have very little stars here, a lot of stars here, and very little stars here. This is what the metallicity distribution is give you, okay? So we do that, and then we see what's the outcome of the alpha over iron versus iron from this chemical evolution model of a very burst bulge, old bulge. So this is what it is. This is calcium over iron, magnesium over iron versus iron. So different alpha elements that work the same way, each other, similar. This is data for the bulge, data for the halo. And this is data for the bulge only for some points that you're seeing here. Here I plot. So there was a work that could observe lancing stars towards the bulge. What is a lanced star? It gets brighter than it really is. So with that, the person could see, Bensby et al. Paper could see stars in the bulge that are subgiants, for which he could get isochrone ages. You know how many? 90. That's what we have the ages like that in the bulge. 80. And then I didn't take his whole sample. I took only the sample of Bensby that's older than 10 gigayears, according to his age. And these are plotted here. So I can reach in an old spheroid high metallicity for very old stars. And this is exactly what I think I'm seeing that plot. I'm seeing this one go. You see? I'm seeing the bulge embedded into the thin disk, the thick disk, the spar, whatever it is. But when the data of Apogee came out, people concentrate too much and say there is no bulge. Okay, so let's not be too fast. There is a bulge, but it's hard to see, you know? So I think we see this here. This is unpublished. We are still working since years on that, but I was waiting Apogee. Another way to see this is the R-Lyra. The R-Lyra are stars that are very old. They are above 10 gigayears, and they are bright. And I can see, I don't need to compute the age because they are old, I know. So it's another way to have the age in the bulge. The R-Lyra also showed this interesting one go in this very beautiful paper by Cristina et al. 2021. Okay, so this is, so up to here what I tell you. In that inner region there were all the components. I can disentangle this chemically and kinematically. I can maybe see an old bulge. And therefore I expect to see the very pristine building blocks of our galaxy there, inside, the oldest. Well, but if this is true, then for which objects can I give ages? Globular clusters, right? So let's study the globular cluster in the bulge. So this is the distribution. Okay. Now I have to switch because I prepare a PDF for this moment. And the part of the animation I need, it's done. So, well, I still have an animation here, but it's okay. Unless it reconnects. It's reconnecting. Wait a second. No, not really. Okay, then let's switch. Conectou aqui. Não sei, deixa eu ver. Mas vai, pode switch que eu vou pegar o resto dali. Tá aí? Então, deixa eu ver. Eu não sei que página eu tô agora. Eu tô... pera, eu tô na página... não tá aí. Deixa eu descer. Mas não tá full screen. É a internet mesmo, gente. A internet desliga, o negócio cai todo. Caiu na hora certa. Ok, vamos lá. Agora feche os olhos. Okay, let me go here. So we're here. Okay, here we are. Okay, so now I want to see where are the clusters, the old stars. Are they there where I think the spheroid is? Okay, so this is the globular clusters that towards the bulge, but not all of them are bulge, but they are towards the bulge. Each point of this is L and B in the sky. latitude, longitude. And here is the shape, you know, when you see the COBE image of the galaxy, that you see this peanut bulge that we have. So this is the form of the peanut bulge that you see into mass. And here is the galactic center, and you have a bunch of clusters, some that are inside the peanut and some that are in the halo around it. Okay, this is in our review. You can look. Now, recently, the Gaia has also, and there are different ways, the way they were discovered and their metallicity, and that's the information here you could see in the oh, sorry, I have to go here to compute. So this, you see, there's a lot of more data appearing here is because of Gaia. Okay, after Gaia and VVV, you discover a lot more clusters. So there's a whole industry of work also here in this area. Because with Gaia, you can really pin down also, for global clusters it's difficult, but you can pin down membership better. So this is a lot, most of the new ones come from VVV, these papers of Miniti, Garro, and so on, and they are going to be in a paper in preparation by Beatriz. Okay, so now let's go back to the bulge. If I put here an extinction map, EB minus V, like the AV I was telling you, this is from another paper, the extinction map of the inner 10 degrees in the galaxy, right? And you see here is very high the extinction. And here you see the bunch of globular clusters that we were able to work together in a project with Beatriz and her collaborators. And these are the little stars here. And you see that they are here. Well, you see immediately that you get spectra from flames UVs if you are not here. Okay, if you are here, you're going to use moons or VVV or whatever, other things. Now, for these things that are in the bulge, but not at very high extinction, we managed to get also, you have then for those, because they are not at very high extinction, they have good proper motions. Okay? With the proper motion, you can select, if you plot the two proper motions in the two directions that Gaia gives you, you plot a bunch of stars, and the clustered in proper motion. So it starts to be an easy job. You have to agree with me, because now, where's the cluster? Here. Okay? And but I had those candidate stars. Well, throw those three away because they are here. But these candidates were chosen in terms of radial velocities. I had a CMD with radial velocity, and these were my candidates. Well, yeah. So you lost your time, because now you should be sitting here. Okay, this is the new thing with Gaia. It's beautiful. Okay, so let's take this beautiful thing. Sorry, wrong computer. And and see if this is true. If the old stars are falling there where they should be. Okay, so here I go back to that diagram, Zmax eccentricity, for the sample we were discussing just before. Okay, the apogee sample, and they are sitting here. Exactly where I expect to see the oldest building blocks of the Milky Way. And then I plot the R-Lyra because I'm going to compare with the R-Lyra is sitting everywhere because there are old stars everywhere. Okay, but there are a bunch here as well. And now the metallicity of the cluster, for example, NGC 6355. If I find, as I said, the mean radius of the orbit, here I'm showing the mean radius of the orbit. The blue is the sample of the apogee at this thing here. The blue is the sample of apogee. The reddish is the R-Lyra, the distribution of R-Lyra, and our clusters are sitting here. They all have a mean radius in the orbit around 1. They are inner galaxy stuff, because this is now in orbit space. They are, I forget about this, and the metallicity, they are more metal poor. But the metallicity has bias. Let's move on. So, okay, I will need a small detour here, and we almost finished, but I need a small detour here. Remember, lecture 1, that the contribution of chemistry will come from different objects. Mergers of neutron stars or black holes that will produce our process elements. Then you have planetary nebula, low mass stars that will produce carbon, nitrogen, and so on. And the type 1a supernova, the type 2 supernova. And this was building our periodic table, okay? So the high alpha, low alpha stuff means alpha elements. That thing I told you work for alpha elements, because alpha elements is mainly produced by type 2 supernova. And iron mainly produced by type 1a supernova. So I have the clock, okay? What's an alpha element? For example, oxygen, silicon, magnesium, calcium, okay? I have highlighted here. They are essentially colored blue, exploding massive stars. You see that the one that's more blue, you now don't see because of this, because I don't have the animation here anymore, but it is oxygen. For silicon and calcium, you have a contribution also of type 1a supernova. So you will delete a bit my clock. My clock will become a bit less good. It's not going to be a Rolex anymore. It's going to be another clock. Okay. Now, you have here, I put a blue box here, vanadium, chromium, manganese, iron, you go to all these iron peak elements, okay? Cobalt, nickel, copper, zinc, they are iron peak elements. They will be mostly produced in the type 1a supernova. They will come later, okay? But you see all the graphs here. This is colored by the main contribution. It's a very nice paper by Kobayashi. You see that exploding white dwarfs is what a type 1a supernova are. But you see that, for example, you have contribution, of course, from exploding massive stars. A little bit. No? Okay. And then, sorry, you have, now I'm going to complicate it, because I have the whole periodic table. Why should I study only alpha and iron? No? I have to learn about the periodic table. Now, here I have cerium, neodymium, and now you are getting like, oh, I don't even know the name of these elements. Yeah. They are S-process elements. And they will be made in, what matters for us here is they will be released to the interstellar medium on longer time scale. Similar to iron, okay? But then, because nature plays not easy with us, what I said is they are S-process elements at the sun. And that is a bit of R process. R process is like coming from type 2 supernova or neutron mergers. So it will come immediately. It's again a clock that became a bit complicated. So if you have good signal to noise, good data, you can use them. If you don't have, forget it, okay? So we are reaching a situation where we can go here. Okay, that was the detour. Let's go back now. We had this alpha over iron are in this plot. I told you, alpha over iron. Examples, oxygen, magnesium, silicon, and calcium, okay? I have the data from Apogee here for our RPM sample. You've seen the two blobs, no? And now here, this blue thing are the R Lyra, the old R Lyra. They are sitting here. These are the people I know they are old. The Apogee have no idea of their age. But I know the old people are sitting here. And now I have the stars, the clusters that I was telling you, sitting here too. You see? Oh, old. Beautiful, you know? And now I say, oh, but what's happening with the R Lyra? Now, what's happening here, right? There are difficulties. That's why you have to look to a lot of data sets. Is this a difficult, or is because there are some R Lyra in debris that were accreted to the bulge and they would have low oxygen override? You see, you cannot go like one way. It's a complexity beautiful here. There's a lot of story here. Okay, now this was the easy bit that you see. Now I go to iron peak elements. If they are iron peak, they should behave like iron. So if I do an iron peak divided iron versus iron, I should get a flat curve, okay? But it's not exactly like that, because there are contributions different. There are details of nucleosides that matter. And the data is telling me vanadium is more or less flat, manganese is going like this, cobalt is going like this, copper is going like this. Interesting. Look, the stars and the globular clusters are sitting more or less in the same place. And these are curves of chemical evolution models, now not by me, but by Beatriz with Amancio Friassa, where you do a very fast formation of the bulge. And this is a curve where a node bulge, similar to the one the toy model showed you, and you are right in the data, you see? So there is a node bulge in the galaxy, even many people do not like I say that. Okay, now you can go more complex than that and go to cerium or neodymium, okay? Now you start to have other problems because it's not easy to get the abundance for this data, right? So here I'm showing data from Salesiva et al. just submitted. And this is neodymium over iron versus iron. For the bulge RPM sample. So what he did, he cross-matched our RPM sample with the star, with Gaia, and with the stars for which they had another pipeline that was able to give good abundances, and got the abundance for those stars. This is what there was in the literature. This is what we are getting here. I mean, if you do a chemical evolution model and you come to me like this, or you come to me like this, it's a different story, right? Now, why is this like this? Is just a question of data, or is a question of sample selection? And here's the complication. Because here I am using stars from the RPM sample, so I am in the bulge inside, very close to the midplane, right? Here, I don't know where was exactly each of these windows. So there are two things here that matters, and that's why it's complicated. Okay. Beautifully also what happened to cerium. This is the data before, and this is the data now. And this is the low alpha part of the RPM sample, this is the high alpha part. So now we are starting to open the box. You have orbits, you have this chemistry, you can go away from alpha elements, right? But of course you're not gonna make a paper forget of the alpha elements. Because I mean, if you come with an explanation to here, but your alpha over arrow is wrong, forget it. Because you have alpha over arrow, you have to look to it. So it's a multi-dimensional problem. You have to look to it. Okay? So I wanted to finish. I don't know how much time I spoke. 50. Okay. So I will kind of finish here. The key points I wanted to bring to people here doing galactic first. Gaia plus spectroscopy has made possible to get precise distance in our galaxy, and this is a breakthrough. That's why Gaia is there. Because if I don't have precise distance, all what I show you, I cannot tell you where the stars are. I am going to always see the box and start seeing, if I have to put some people are doing like this, I have to be in the bulge, I go down in the plane, and then I look only to the above the plane. It's a different way, but we can go more than that now. We don't need to be doing like this. We don't need to be only doing analysis in L and B on the sky. We have the 3D, we have the orbits, we have the data, we can put the globular cluster, we have everything is is a crazy moment for galactic archaeology, I can tell you. You want to do so many things and there is no time. Time for research, nobody has found a way to increase our days yet. So Gaia plus spectroscopy made this possible, and we found this beautiful velocity quadrupole in the inner part of the galaxy, as I show you. The bulge now can be studied in orbital chemical space. There are caveats. I show you caveats in the pipelines, caveat in the potential that I use to compute the orbits. That's why I have to compute the orbits in several potentials. See if my results are robust, even though I use that potential. That's what we are doing. I have to complement samples because I don't. Where the bulge is coming up in this sample, I had 200 objects. I want to have thousands of objects there. There was another thing up there that even didn't say, which is for the next, that's why the bulge is 2 lectures, is the fact that when we go to the upper part and where we are seeing the bulge, high Zmax, high centricity, we also see a counter-rotating population. So there is a debris there too. A galaxy that was accreted to our galaxy and is now, we see this, you see? And that debris has chemistry. And that debris doesn't have high alpha. You see, so it's like you cannot stop. It's really hard, and this is yeah, you just work like this. So the objects confined in the inner 4 kiloparsec, they show a very metal-rich thin disk. They show a thick disk population with large velocity dispersion. Also, this old bulge buried inside the bar and the inner disk. The globular clusters in the bulge possible. Why is the globular cluster nice? And I haven't showed the plot. Forgot. I don't know what happened. I have the ages for these bulge globular clusters from the CMD, because the globular cluster is easy to do a CMD age. And in this paper, Souza et al. That we did with Barbui and her student, he had HST data combined with flames data. So in the end, he had the age of the bulge globular cluster I was telling you, and guess what? It's 12.5 gigayears. The oldest globular clusters in our galaxy are in the bulge. NGC 6522 is almost 13 gigayears old. Where is it? In the bulge. You see? So, if I ask you, where should I study the chemical properties of the oldest stars in the universe? Where? Yeah. Or I take JWST and go high redshift, but then I don't have the chemistry. Okay? So, that's the point. So JWST is seen at redshift 5, but we are also seen here at redshift 5. You just have to look for it, you know? Okay, so they are very old. We find no chemical segregation of stars in bar-shaped orbit. Now you understand the sentence, because that's the way it says. So in the bar-shaped orbits, you have everybody. That means the bar-trapped stars at some point. Now, when was the bar formed? If you have the age of the stars in the bar, can you tell when the bar formed? There will be a spread in age. No, you cannot. But if you have the age of the youngest stars in the bar, you can. Okay? So that's how you have to think. We find no camera. The ones with low Zmax are migrator candidates. They present the largest metallicity, but an important component of metal pore is also present down there, right? We see at the solar neighbor that stars that have migrated maybe from there. Now everything is closing. It's so beautiful. I am so happy to be here. I would be happy to do my PhD now, you know? But now that was done many years ago. We need to move in the future now, because we need to move in the future to answer Simone's question. We were with very few data. We will need foremost, we will need Plato, we will need Guyanese infrared, Hedin. And now here comes the bad news. Finger crossed for Hedin. We passed several phases, but apparently we didn't pass the last one. And this is also something, I don't know if it's public, so okay. This is something, because we are in a PhD school, that you have to be ready to fail. You know how many times we fail, make a proposal rejected. But what's beautiful? What did my proposal bad? No. Fail. There's a bunch of people that want to use that telescope. Try to make it better the point, but even like this may fail. You're not going to fail yourself because your proposal failed. Now we work like crazy for ESA. You cannot imagine. We got select for phase 0 for a ESA mission, a satellite that was going to do seismology in the bulge, and we'll come to this plot with age 70,000 stars. I'm still sad today, but I mean, we work like crazy. We fail. Why? What happened? Well, there was a political, I don't know, there's many things. It's like we talk about 500 million euros something, you know? It's not like, oh, but I want because my proposal was good. Oh, yeah, it's like that. Oh, why did you work on that if the thing will be up only in 2040? Well, because if I don't do, who's going to do? I'm going to do for you guys to use. And that's the beauty. That's the beauty. Somebody asked, why in one of your talk, now I'm going to go political here. Sorry. But somebody asked, why in one of your talk in the bulge in Pucón, when I gave a review, I had, it was, the day I was giving the talk was the 70 years of the document of the human rights, okay? The letter of the human rights. And Lula was in prison. So I said, how can I give here a talk? It's the 70 years of the human rights, and Lula is in prison without having to do anything. If you disagree, it's fine, okay? But that's how I see it. Because science is this. Science is democracy. Because I'm doing my piece here today for somebody else to pick it up, for somebody else to pick it up, for somebody else, because we are getting old, you know? And I'm here preparing Guyanese infrared. Guyanese infrared is still on the go. It was not cut yet. I'm here preparing Guyanese infrared, and this is going to fly, if at all, in 2045. Just compute your age. 2045, it starts getting the data. The data will be useful in 2055, if everything goes well. And shall I not think about Guyanese infrared? Who's going to think? Who's going to go there? To do Guyanese infrared, you have to have been working the data. And you have to go there to them and say, this is where we are. You know? So I just wanted to, get this awareness that at some point, you have to pick it up from where somebody else left. So join. I heard many times some young people saying, oh, but we are going not to working for the surveys because it's a lot of work and, you know, it doesn't give me a permanent position. well, it doesn't give you a permanent position today, but tomorrow, say, oh, that guy, he was in that survey, he was doing this. You know, this is what you have to do. And to participate in all these big projects without really always want to win, because it's not going to work. No? And that's what I try to do. Okay? And it's a lot of time. That's it. Thank you.
Thank you so much, Cristina. Very nice lecture. So, we are a bit late, but we have time for one question. Two questions, okay.
Okay, I had two, so I'll just make one. You kind of answered it already, because I was going to ask if we should expect to find accreted populations in the bulge, and you already answered that. Maybe we... Yeah, next lecture. But should we expect these accreted populations to be older than the accreted populations in the halo? Like they should have been accreted in the earlier stage of the formation of the Milky Way? Or how did they get to the bulge? That's my question, actually.
I think they will be older, because, well, I don't know, because they need, if they are in the bulge, they have phase space mixed, and that's what I'm going to show. You cannot, for example, when you're going to do something in the halo, you put in the energy angular momentum plot, and you can see the blobs. But if you go to lower energy, so they are phase space mixed, you lost the information already, and that's the way to find it.
Okay,
then maybe they are phase space mixed because they are older, but there is the mass, how they enter the galaxy. There are many other parameters, so I don't know.
So, last question.
Okay, so Cristina, Gaia gave an amazing contribution with distances and proper motion and so on. But can you say that maybe ages are the next parameter to
They are the next, and that's why I'm so sad today.
Okay.
They are.
Okay, so if you have another questions, you can meet Cristina during the next coffee break. Okay, so let's go to the boat, to the lunch, okay, and see you at 2 o'clock here.